Okay, now let me say something about infinities. If there was not n, but an infinite series. So the case that we've treated so far, the case when there are finitely many terms, is absolutely 100% riskless from the point of view of calculus. You don't have to think about convergence. You don't have to think about anything. You have 2n plus 1 functions. What you're basically doing is a linear fit. It's just that we did it within a product. And this uncontroversially yields the best result. And it's true for any n, no matter how large. So the only question that remains is does the approximation get better as n grows larger? That's more of an analysis question. That's more of a linear algebra question, but when you step into the infinite dimensional spaces, this is where Hilbert spaces, as they're called, play a central role. This is why they were invented, to answer this very question, to basically extend linear algebra to this infinite case. And the answer turns out to be yes. Well, from linear algebra we know that the more as n increases, things can only get better. I think we know that. Because when we're looking for a minimum, if we got this close to the function, this close to the answer with 2n plus 1 functions when n was small, surely we can only get closer if we have more degrees of freedom. So I think it's almost unequivocal that the larger n, the better the answer will be. But when you go to infinity, what happens? So when you go to infinity, there's very good theory for Fourier series, that it actually, for a very broad range of functions, it actually converges point-wise to the function f of theta, if f of theta is continuous. And sometimes it's not so easy for the function to be continuous, because you might think of this function as continuous, but that's not the function you're representing. It's its periodic repetition. And so you might experience an unexpected discontinuity. But in all points of continuity, it converges to the actual function. At the points of discontinuity, it will converge to the average. That's how clean the theory is. And it's beautiful. Okay. So that's one way to think about it. To solve a finite problem, and then within that finite problem, make n go to infinity and get better and better and better result, and then only ask the question, will it converge in the limit? But I think that a freer, more imaginative way to think about it, even though most people will call it not rigorous, but whenever you sacrifice rigor in favor of beauty and imagination, you should always do that. And if you think about it from that point of view, you would say, I immediately have infinitely many sines and cosines. And my basis has infinitely many elements in it. And so what I'm doing now is not least squares, but straightforward decomposition with respect to a unique basis. Not a unique basis, with respect to a basis. So I'm looking for that unique decomposition with respect to the basis. And all I'm doing is using this formula, which, as you know, as we reviewed at the beginning of today, works for all bases. And so that's what I'm doing. I'm thinking of my infinite collection of sines and cosines as a full, complete basis. And I'm simply doing classical decomposition by inner product with respect to an orthogonal basis. So what drives this logic is not calculus, but linear algebra. That's the skill. If I can teach you this skill, I will be very, very happy to approach whatever problem you're working on and to see it as a linear algebra problem. Or if it's not a 100% linear algebra problem like this one is, because it was solved 100 years ago, it's at least partially a linear algebra problem. Then you have to identify that part of the problem you're working on that is a pure linear algebra problem. And basically impose this linear algebra framework on whatever problem you're thinking. If I were teaching tensor calculus, I would say, learn to impose the tensor calculus framework on whatever problem you're doing. If I were teaching probability and statistics, I would say, find the probability and statistic crux of every problem. So whenever you're learning a good subject in mathematics, you usually find the ability to see any problem in the world as a problem in that topic.